Welcome to Study Loop.
We are going to find the volume of the largest rectangular box in the first octant with three faces in the coordinate planes and one vertex in the plane x plus 2y plus 3z equals 6. So what we have here is a situation like the following. We're going to depict what's happening here. So we have, let's say, we have the axis here. This is z-axis upward, positive direction upward. And we have here x-axis positive to the right, and the y-axis coming here. This is a positive direction. So this space here with this corner here at 0, 0, 0, the origin is the first octant, in fact. That is, the first octant is defined by all the variables positive. So we have a point somewhere. So if we draw this box here, for example, so we will have a face on the plane. Just do it better here, like that. So we have this face here in the plane yz, and this other face will be in the planes xz, and the third face we have in a coordinate plane is in the plane xy. So we get this face here, something like this. So this rectangle here is lying entirely on the xy plane. This other rectangle here is lying on the xz plane, and this other rectangle is lying completely in the plane yz. Then we will have another face here somewhere in front of the face that is parallel to the face that is in the plane xz. Then we have this other face up here in front of the face that is in the plane yz. And on top of that, we don't have any rectangular face, or we have a face if we think that the box is closed, so we have a face parallel to the face lying in the plane xy. So it's the face in the top here, on top of the box. So this is the sketch of the situation, and this point here will be lying then on the first octant. And moving this point around the first octant, we change the shape of the box. And in fact, the position of that point will determine completely the box, because we project perpendicular this point to the plane xy, and then we will have the box completely defined. So the coordinates of this point will define the box completely. If we don't restrict the position of that point, then we can draw boxes with volumes all the large that we want. There will be no limit to the dimensions of the box. But in this case, that point, that vertex here, this red point, must be on this plane. And that's the condition that's constrained the possibilities of the box to be large or not. We're not going to draw that plane, but we imagine that there is a portion of that plane that lies inside this first octant, and from all the points inside that or on that portion of the plane, we can choose the vertex of the box. So that's more or less the situation. And that we want here is to find the volume of the larger rectangular box, that is the maximum volume. So the function giving us the volume, if we consider this vertex with coordinates x, y, and z, will be x times y times z, because we know the coordinates of the point or the vertex in the first octant will determine the dimensions of the box. The coordinates of that point will be the dimensions of the box, in fact, and that's possible overall because the point is in the first octant and all its coordinates are positive. So we have this function here with three variables indeed, but we know that the point got to satisfy the equation of the plane x plus 2y plus 3z equals 6. So from here, we know that the x, for example, got to be equal to 6 minus 2y minus 3, 6. And so the volume of the box will be given by x, that is 6 minus 2y minus 3c times y times c. And that's the function that we get to study or use because now we have two variables. That is, this is in fact the function of y and z given by 6 minus 2y minus 3 z times y times z. And here we have already considered the fact that the point is in the plane given here. So we would like to find the maximum value of this function, and for that, because we have two variables, we get to apply the two steps to find those maximum values, and that is first to find the critical points of the function. In this case, we get to find for the critical points the first order derivative of v, that is partial derivative of v with respect to y, and that is, to do that, I'm going to develop this formula a little bit. 6yz minus 2y squared z minus 3yz squared. And now it's easier to find the derivatives. And with respect to y will be 6z minus 4yz minus 3z squared. And now the partial derivative of v with respect to z at yz is equal to 6y minus 2y squared minus 6yz. And so we got to solve the system of equations 6z minus 4yz minus 3z squared equals 0. That is this partial derivative equals 0 and this equals 0. 6y minus 2y squared minus 6yz equals 0. And what we can do here, for example, is to find y from the first equation. So from 6z minus 4yz minus 3z squared equals 0, we get that 4yz equals 6z minus 3z squared, and we got to divide by 4z. Z it cannot be 0 because if z is 0, if any of the variables in fact is 0, then the volume will be 0, and that's not the maximum value, the possible value of the volume. So in fact, for any of the variables 0, we won't have a rectangular box at all. So all the variables got to be positive, and so we can divide by 4z, and we get y equals 6z minus 3z squared over 4z. We simplify z here, and we get 6 minus 3z over 4. And that's y in terms of c, and then we can replace that from this and the second equation. We replace that here, and so we get 6y, that is, we don't put 6y, but 6 times this expression here, 6 minus 3z over 4, minus, and in fact, I'm going to simplify a little bit before I substitute the expression of y. That will be better. So we write here the equation 6y minus 2y squared minus 6yz. We can say that is equal to y times, in fact 2y times 3 minus, and we have y minus, and then we have 3z. And with that, we write y twice only. And so 2 times 6 minus 3z over 4, we're replacing now y here from this, times 3 minus y, that is 6 minus 3z over 4 minus 3z. And that's equal to 0, because remember the equation is this one here. That expression equals 0. What we did here was to simplify or take y common factor. And this implies that 6 minus 3z over 2, simplifying this 2 with this 4, times, and here inside we do the operations, is 4, 12 minus 6 plus 3z minus 12z equals 0. And now we multiply the fractions. We know that it's the multiplication of numerator times numerator over denominator times denominator. So the denominator, which is 8, we pass it to the right and we get 0 again. So we can say that this is 6 minus 3z with this factor here out. And on the right we have 12 minus 6 is 6. And 3z minus 12z is negative 9z equals 0. So from here, we have two possible solutions. So we can say that 6 minus 3z is 0, or 6 minus 9z is equal to 0. From this, we get z equals 2, and from here we get z equals 6 over 9, which is 2, sorry. 6 over 9 divided by 3 is 2 over 3, 2/3. Let's see if this solution has sense. And we can see that if c equals 2, then y equals, and we replace here in this equation here, 6 minus 3z, that is 2 over 4, and we get 0. And this has no sense because we said already that neither or none of the expressions or variables x, y, z can be 0. So we can say, so the only critical point to consider is z equals 2 over 3. Then y equals, we use the same formula again, 6 minus 3 times 2/3 over 4, and that is 6 minus 2 over 4, and that is 1. And to find the other coordinate, we use the fact that the point is on the plane, in the given plane, so it's the formula here. 6 minus 2y minus 3z. 2y, that is 1, minus 3z, which is 2/3. So we get 6 minus 2 minus 2, that is negative 2. Sorry. 6 minus 2 is 4, minus 2 is 2. No, negative. It cannot be negative. In fact, it's not negative. It's me that made mistake. So it's 2. So x is equal to 2. So the dimensions of the box are 2, 1, and 2/3. But now we are going to verify that in fact we have at least a local maximum with this point. And to do that, we use the second order condition, in which we use the second order derivatives of the function. That is, we calculate the second order derivative of the volume with respect to y and z. And the second order derivative with respect to y is the derivative of this expression here with respect to y, and we can say that this is negative 4z. So we have negative 4z and if we do the same for the other variable, that is the second order derivative with respect to z twice, is negative 6y, and the mixed second order derivative with respect to y and z, which is the same if we do it in any order because we have continuous derivatives, they gotta be equal. And this is 6 minus 4y minus 6z. And so here we calculate what we call the determinant of the Hessian matrix, that is d of x of yz, is the expression second order derivative respect to y times the second order partial derivative respect to z minus the square of the mixed second order partial derivative. And if this is positive, then we gotta see the sign of any of these two factors. If it's negative, we will have a saddle point. If it's zero, we don't have any conclusion to draw. So here we say this is equal to uh, negative 4z times negative 6y minus 6 minus 4y minus 6z squared, or 24 yz minus 6 minus 4y minus 6z squared. But we don't have to calculate this in general. We don't have to expand that, and that's the kind of thing, because what we want is the evaluation of this determinant at the critical points. In this case, the only critical point to consider, which is y equals 1 and z equals 2/3. Maybe I said something that is not correct here in strictly critical sense, is that I said that the critical point to consider is z equals 2/3. In fact, the critical point has these two coordinates. So the only critical point to consider is the point 1 2/3 with those two coordinates. So I get it. If you want, you can write that correctly here. And having said this, we can say that the determinant at the critical point 1 2/3 is equal to 24 times 1 times 2/3 minus 6 minus 4 times 1 minus 6 times 2/3 square, and this is 24 over 3 is 8 times 2 is 16 minus 6 minus 4 is 2 minus 6 over 3 is 2 times 2 is 4 square, and this is 16 minus 2 minus 4 is negative 2 squared is 4, so we get 12, which is positive. When the determinant of the Hessian matrix is positive, we will have a local maximum or a local minimum, and that depends on the sign of any of these two factors. They will have, in this case, the same sign. So we will let any of them, and we see the sign of that factor. So the partial derivative of v with respect to y twice at the critical point is, let's see the equation, we get negative 4z here. So it will be negative 4 times 2/3, and that's negative number. And we have a negative number in this coefficient. It means that we have a local maximum. The critical point, and here I'm going to write it correctly, in fact, the critical point 1 2/3 is a local maximum of v of yc. That is, we have turn or convert this, transform this function into the function of two variables. We have applied conventional calculus to find the critical points of the new function of two variables. We have found two possible values for the coordinate c, but one of those values uh, leads to a null value in one of the coordinates, which doesn't make sense. And for that reason, we have only one critical point. And using second order conditions, we verify that the point is at least a local maximum. Here we are not proving that it's a global maximum at the first octant, but we stick with this verification here in order to say that this is our solution. And so we can say, conclude that then we can say that the largest rectangular box constructed as specified will have to have dimensions 2, 1, 2/3, that is in x, y, and z. The maximum, that is the point, the vertex in the first octant we gotta take is 2, 1, and 2/3. And the maximum volume being 2 times 1 times 2/3, that is 4/3. And the point 2, 1, 2/3 is in the plane specified in the statement of the problem, and that's the point giving us the maximum or the largest volume. And the box is constructed taking the vertex 2, 1, 2/3, which is in the first octant because all the coordinates are positive.